Well, hey guys, I promised you I would do an example of the mixing problems that I tried to describe during class as an application of first order linear differential equations. And I didn't have time to do it during class, so I'm just going to show it to you here. It should be a short little video. Remember that we're interested in the amount of chemical in the solution as a function of time. And of course it has a rate of change with respect to time, which is why we have a differential equation. And that rate of change has to do with R1, C1, R2, and C2. Those are the flow rates and the concentrations of the chemical flowing in and out of the tank. Okay? And remember that the C2, which is really the concentration coming out of the tank, is really just A divided by V. V is the volume, so you see A over V right here. And so the volume, remember, is just some initial volume plus R1 minus R2 times T. So it's going to look something like that. So we have a problem here, and we need to just read it very carefully. We initially have 600 liters, and we have 1,500 grams of salt in the solution. And flowing into the tank, we have a solution with 5 grams per liter, and it's flowing in at 6 liters per minute, and flowing out at 3 liters per minute. So a lot of this is just figuring out which number goes in which place. Okay? So, for example, the 600, that's just going to be the initial volume, right, down here. The 1,500, that's just the amount of chemical at the start of the process, A of 0. Let's see, 5 grams per liter is flowing into the tank, so that would be C1, right? The concentration flowing into the tank in grams per liter. And the rate at which it's flowing in is 6 liters per minute. That's the R1, okay? The mixture flows out at 3 liters per minute, so that's the R2. Okay? So if we put all of that together, we can just set up our differential equation, dA dt. Actually, let me make sure that this is showing up on the screen there. dA dt plus R2, which was 3, divided by V. The V is going to be V naught plus R1 minus R2, which is 3, times T. And all of that gets multiplied by A. And then R1 times C1 is 5 times 6, that's just 30. So here's our differential equation right here that we need to solve. Okay? And as I explained, this is always a first order linear differential equation. Okay? I'm going to go ahead and erase these values here for a moment. We'll come back to those things if we need them. The first thing that I can do to make this a little bit easier is I can take out factors of 3 from the top and from the bottom. So if I just divide everything through by 3 in this fraction right here, everything else stays the same. This is what it would reduce to. Okay? So remember, my first order linear differential equation has this form right here. Okay? And so in this case, the P is really a function of T. Okay? So I'm not going to have an X here, I'm just going to have a T here. And so my first step to solving a first order linear differential equation is to find the integrating factor. So the integrating factor, remember that's I, is e to the integral of P of t dt. If we use t for our variable. Okay? So this is e to the integral of 1 over 200 plus t dt. And that's going to give me e to the ln of 200 plus t. I'm leaving off the absolute value bars because I know that 200 plus t will be positive anyway. And I'm also leaving off the plus c. Remember that when we find integrating factors, we don't have to include a plus c on that. And the e and the ln cancel each other, and I find out that my integrating factor is literally just 200 plus t. Okay? 200 plus t is my integrating factor. So, what do I end up with? Remember that we take that integrating factor, we multiply it by the unknown function, and we have a product rule derivative that is supposed to equal the right-hand side, which was 30, times the quantity 200 plus t. That's going to just look like that. All right? So we take that thing right there. Let me make myself more room. The nice thing about the video, you can rewind it at any moment if you need to and watch it a little bit more carefully. I simply now have to integrate both sides. So when I integrate on the left side, I can just cancel my derivative. And when I integrate on the other side, I'm just going to do this quickly for you. It's a very simple integral to do. I get 15 times 200 plus t quantity squared plus c. Okay, great. So this is what we have so far. So the amount of chemical, if we wanted to solve for the A of t, I could just divide through by the 200 plus t. I would get 15 times 200 plus t, and then plus c divided by 200 plus t. Now, you may remember we were given an initial condition. Initially, at time 0, the amount of chemical is 1500. So I know that if I put in 0 for t, I should get 1500. So 15 times 200 here, plus c divided by 200 right here. This is what it should look like. Okay? So this is going to be 15 times 200 is 3,000. So this is going to be 3,000 here. We can subtract it from the 1,500 and we'll get negative 1,500 equals c over 200. In other words, c is equal to 200 times negative 1,500, which is what? Negative 3 with a lot of zeros after it. Negative 300,000. So it should be something like that. So far, so good. Let me just see here. This is not quite coming out to what I thought it was supposed to. Yeah, I think it looks okay actually. Right, okay, so that's what we would have there. So we get A of t. Actually, I need just a little bit more room. Come back over here again. We get A of t equals 15 times 200 plus t. I'm just recopying what I have over there. And then minus 300,000 over 200 plus t. Okay. So this is what we would have so far. All right. So let's make sure that makes sense. We put in 0 here for t. We got 15 times 200 plus c divided by 200, and we set that equal to the initial amount of 1,500 grams. Okay, this is what we have so far. All right. So from there, we have the amount of the chemical, but we have to read the question very carefully. It says find the concentration of the chemical. So the concentration, remember, is the C2 of t. And for that, we have to take the A of t, which is 15 times 200 plus t, minus 300,000 over 200 plus t. And we have to divide that by the volume. And the volume in the tank, if you remember, we wrote it down earlier, it was 600 plus 3t. So this is actually the concentration at any time t. Okay, and now we just simply have to figure out what the time is that we're supposed to use. And that is after 1 hour. 1 hour is just 60 minutes, so we would put in minutes because everything else in the problem was given in minutes. We would just put in the 60, So we would get 15 times, well, 200 plus 60 is 260. Okay, minus 300,000 divided by 260. And then all of that would be divided by, well, let's see, 600 plus 3 times 60. Well, that's going to be 780. Maybe something like that. Okay, so this is going to be the answer. Whatever that is, that would be in units of grams per liter. Okay, so at any rate, again, it's a pretty simple process. You just have to put the right numbers into the right places, and then you come up with a very simple solution to the problem. Okay, if you have a tank that's initially full of water, then in that case you have an initial amount of 0. So one of the homework problems has water in the tank to start off with. There's no chemical at all. So be sure to use this for the initial condition when you're solving for the constant. Otherwise, I don't think there should be any other real tricky aspects to that particular kind of problem. Be sure to ask me if there's any questions about this. You can rewind, watch it a little bit more. I hope it all makes sense, and we'll see you again soon. Thank you guys very much for paying attention.